Hi everyone. So today we are going to solve another problem that is generally asked in machine learning system design interviews. That is people you may know. Uh, Before starting the video, I would like to tell you what I am going to cover in this video. Initially, I'm going to cover the objective, that what exactly this problem is. Second is the input and output of the system. Third would be the data engineering part, where I'm going to tell you that what data do we have, and fourth would be the feature engineering part, where how to convert that data into features so that these features can be used for your model. Fifth would be the model development part, uh, where I'm going to tell you that what kind of models we can use to solve such a problem. Sixth would be the evaluation part, where I'm going to tell you that once you train your model, how to evaluate it, whether it's good or bad. Seventh would be to the last would be the serving part, where I'm going to tell that how we are going to serve it to the end users. Okay, so coming to the objective. See, the objective is something like so whenever you open LinkedIn, you see that you see options that it shows that to what users you can connect with. We are solving the same problem, that whenever we open our platform, it should show n number of k number of connections to us which are relevant to us, uh, through which we can connect to, so that our network increases. Okay, now this is the problem that we are solving. But how many users do we have? Let's talk about that. Let's set some constraints. So consider that we have around 1 billion users on the platform, and consider that 300 million users are active users. And what other things that are there on platform are same like LinkedIn. Like you can send a connection request, uh, you can like a post, comment over a post, share a post, then you can share the profile, then you can just view the profile, uh, you can ignore the user, like sorry, block the user. Okay, so the same things which you see generally on a LinkedIn platform, the same stuff would be there. Now this is the objective. Now coming to the input and output of the system. So here if you see, the input would be the user itself, and output would be the recommendations of different people that are relevant to him. So input is just a user, like let's say it's me, and there is this service, uh, PYMK service. PYMK stands for people you may know, and it shows top, let's say 50 connections to us which are relevant to us, to whom we can send the connection requests. Okay, so this will be the input output of the system. Now coming to the third part, that what data would we have. See, here generally you need to think very logically, of what data generally do we see on LinkedIn. So consider that with respect to user. So with respect to user, you have his age, gender, you have his his or her education details, then the industry that he works in, whether he works in software, whether he works in finance, in what particular field he is working in. Then it could be uh, something like that, how many days it has passed that he has made his account. Then it could be something like his company name, where he works. um, like you can think of all other features as well, but even like let's say the number of connections he has, he or she has, uh, then I guess these many features are enough for a particular user. If we think of other features, we are gonna add them, but for now we have such data for a particular user. The what other data we can have? We can have the connection details about a user. So for example, uh, user connection. So for example, what I want to say is that what particular user id is connected to what particular user id and when did they connect. This is just the data that we have. We How to convert this data into features is something which we will think in the later stages, but currently we have such data. Then it could be something like that, uh, user interactions with the platform. So see, when we say that user interactions, what does it mean? You can search a profile, you can share a profile, you can send a connection request, then you can accept a connection request, you can like someone's post, you can comment over a post. Such things will you see, you generally do it yourself, right? So but how would the data eventually look like? So it would be something like, here this user id, again a different user id, for example user id a sends a connection request to b, right? Then the interaction type would be sending a connection request. Then what there could be an interaction value also, right? So for example, if he comments over a particular post, then a uh, commented over a post, so what is the comment, right? So here for this case it would be null. And at what timestamp uh, did he do that, right? So all these things could be there in the data engineering part. Now the question comes that how are we even going to take care of this data uh, to convert them into features? Okay, so feature engineering. See, before jumping into features, the first doubt that generally comes in everyone's mind is that hey, we have two users, okay, and somehow we convert this, but we have this data with us, right? Right, for a particular user, we convert them into features, and what we do is that we just do a dot product between them and calculate pointwise similarity. Ki how much similar are they? So for example, if two people are working in the same company, same education, then yeah, they have high chances to connect, right? We should show them as a recommendation. But don't you think that here we are not considering their social graph? What does this social graph even mean? So for example, let's say there is this user b a, and he is friends with b and c, and then b, he's a friend of d and c, okay. So don't you think that a should be also, a should have a recommendation of d as well, right? Means if I am showing recommendations to a, then d could be also a possible recommendation. So this means that we don't have to just consider his features, we have to consider the other features, neighbors feature as well, to make sure that we are showing all the possible recommendations that are there, right? So we can't just go with a pointwise similarity kind of stuff. We need something a bit complex which takes care of neighborhood stuff as well. Here neighborhood means with whatever people this guy is connected with. Okay, so now the question comes that, hey, how are we even going to do that? So let's divide into two things. First thing is that somehow we need the user features, and then we need something as social features. Social features means, okay, how many so let's say here if A is there and B is there, how many connections are there between them? Did they even study in the same college or not? Did they did A study in the same college as B? Did A works in the same industry as B? Such kind of features could represent in the social features, and user features would be something which are related to a particular user only. So now first thing is that how we will convert the user data into features. Let's see that. So what data uh, did we have with respect to the user? So let's just bring it, and one by one let's think how we are going to convert that. So we had this particular stuff. Let's copy it and let's paste it. Okay. See, the first thing that comes is that age. Now age, the thing you can do with age is that you can bucketize plus one hot encode. Now what does this mean? So let's say you have some categories 10 to 18, 18 to 26, 26 to 45, sorry, 35, 35 to 42, 42 to 50, 50 to 80. Okay, so let's say if a user comes of the age 19. Now how I'm going to represent that particular user? So he would be represented something like 0 1 0 0 0 0, because the one came from here and all others were represented using 0. So this is bucketize plus one hot encoding. Then comes gender. Again, the gender could be male, female, and other, right? Now the problem with this male, female, and other is that sorry, not a problem. The simplest solution is that you just apply one hot encoding. So for example, if a male is coming, you can represent him by 100. So he could be presented using a 3 dim vector 100. Okay, then comes education details. Now see, in education details there could be few things. For example, the person did computer science from Triple IT Delhi, from the year 2002 to 2006. Okay, now see, here the thing that you can do is that to understand the semantic meaning of this, that what did he do and what college he went to, the simplest solution that you would do is that you pass this computer science, this Triple IT Delhi, from to a pre-trained model which could represent this in a vector of, let's say, 8 dims. Like 8 dims is just an example that I want to say. uh, the, the, the the thing which you are trying to solve is that you need to understand the contextual meaning or semantic meaning of this computer science stuff. So for example, if someone would have done just computer science and mathematics engineering, so he and that person are quite similar, right? So we need something which uh, we need such embeddings which try to bring that two vectors which are like closer to each other because they are same. right? Computer science and mathematics. So we can pass them through a pre-trained vector, which converts them into a 8-dim vector. Now, what pre-trained vector you can use? Simply, you can use a model like sentence but, or some model by OpenAI, which is open source. You can directly use that to convert them into a 8-dim vector. So let's say the education details again could be represented using a 8-dim vector, which are coming from a pre-trained model. So you don't have to train anything here. Then comes industry. So in industry, again, uh, how many types of industry could be there? Like finance, software, accounts. Accounts would be just related to finance, but marketing and many more, right? So there could be like 200 categories to it. And we know that, so there is this rule of thumb which I have taught in my previous videos, where what you can do is that if you want to convert anything into embeddings and you want to know what will be the embedding size, the simplest thing is that you apply this rule of thumb which says minimum of 50 comma square root of n. So square root of n means square root of 200, where it's roughly 14, right? So it means that these 200 categories could be represented using a 14-dim vector. But do you need to actually train these embeddings? The answer would be no. Again, let's say if you can pass the education to a pre-trained model which understands the semantic meaning, in the same way we can pass this industry as well, which gives me a 14-dim vector which understands the semantic meaning. Okay, so again, this particular stuff could be presented using a 14-dim vector. Now, let's say how many days uh, he made the account. So why did I even choose this particular feature? See, the thing is that if it's an old account, it would be more trustable, right? So for example, if you are on LinkedIn from past 8 years, and if some new user comes which is just like 3 days ago, that user would be more suspicious to connect with rather than a user who has like who is on that platform for 8 years and he has added all his details, right? So now generally the date would be like 300 days or 400 days. Now how would you take care of how would you convert this into a feature? So what we can do is that we can apply min max normalization here. So something like 400 minus min by max minus min, where max and min are max could be how what is the maximum time a person was there on the platform. So there would be someone who was from the starting day of the platform, something like that, and min the same way. So it could be min max normalized here, generally just a one dim quantity. Okay, so this is again a one dim quantity. Again, if you want to go with a company name, the simplest answer for company name is either you could just represent into embeddings, or uh, I would say just represent it using embeddings. You can pass it through again a pre-trained model and just get a 8-dim vector for that. Okay, then comes number of connections he or she has. So for example, why is even this particular data taken? So let's say if there is a person who has like, let's say 5,000 connections or like 50,000 connections, they are a lot, right? So generally people would connect with popular accounts. So it's better we convert this into a quantity which is low, because if we give such big quantities, the model would eventually have the problem of exploding gradients. We don't want that, right? We need to convert this into something which is very less in quantity. So you can just represent by log of 1 plus connections. This is how you convert such features. they would normalize it to a very less quantity so that my model doesn't face this exploding gradients problem. Then these are the things through which you can convert this user features. Now let's consider that when you concatenate all the features, it would be something like a vector which you have, let's say a 50 dim vector. I'm just taking an example that all the user features one concatenated could be something represented in 50 dims. Okay, now we need to take care of social features also. Now what social features am I talking about? So social features, so these are pretty straightforward. So social features are always between two users. So the first question you can ask is, are they in the same company or not? Then the other question you can ask is, are they in the, it could be simply printed by using 1 or 0, right? Then you can ask that same industry or not. Then you can ask that they were in the same college or not. Because generally what happens is that if someone is from, let's say, IIM Ahmedabad, and there is another connection who is again from Ahmedabad, but he is a senior, they generally tend to there are high chances that if we show him that recommendation, he would connect to that particular user to grow his networking, right? Then comes what were the overlapping years in the college. So for example, when I said that there is a college senior, so it is possible that he was from the batch 2002 to 2006, and then you were from the batch 2005 to 2009. So there is one overlapping year, right? And if there are overlapping years, then it certainly means that he is either a senior or junior to you, and you there are more chances that you connect with that individual. So uh, okay, then you can ask this question, that number of mutual connections between them. Now see, let me give you an example of how to convert this particular quantity into a feature. Okay, so let's say A has 100 friends on the platform, and let's say B has 100 friends on the 100 or 1000 friends on the platform. Okay, and there are just three common uh, friends between them, just three. Okay, so do you think there are like high chances to connect? The chances will be very less, as if there would be 30 or 40, then the chances would be much high, right? So number of mutual connections increases the chances of a person connecting to another person. But at the same time, let's say we need to apply such a normalization which takes care of uh, like other things. For example, let's say A has 10 friends, B has again like 10 or let's say 5 friends, out of which 3 are mutual. So here you see there are very high chances that A and B can connect, right? So how do we normalize it? So we apply min normalization here. So min normalization, the formula is very simple. Number of common friends by min of A connections, minimum number of A connections, minimum comma B connections. So for example, here it is 3, minimum of 10 comma 5 for this particular example. So it would come like 3 by 5. So which would come 60.6. So you see the chances, the value is pretty high. So it means the chances of connecting them are pretty high. So okay, then comes uh, shortest path between two connections. Now, what I mean to say, let's say there is this guy A, there is this guy B. Now, A has a friend C has a friend D has friend B. Okay, so you see, how many hops do I need to reach this point? 1, 2, 3. For so it's like three hops. 1, 2, 3. Three connections later, I was able to reach B. Okay, so if the connections are very short, then there are high chances to connect, right? But how do we convert this into a feature? And the other thing is that how do we calculate the shortest path? See, for shortest path, the simplest algorithm that you can apply is BFS, right? So for every other user, you can calculate how much distance is from A to B. So the answer comes to be 3. Okay, but then how would you categorize this? So let's say if it's like one hop, so I would say that you can categorize plus one hot encode. So what does this mean? Let's say there are four categories we made: one hop, two hop, three hop, greater than four hop. Okay, so if for example, if I'm talking about D, so he would be presented using 0, one hop, two hop, sorry, so 0 1 0 0, right? So you see, this could be also represented into such particular thing, a 4-dim vector. So overall, you see that you were able to convert these things into features, but these features are social features, and social features will help you uh, take care of your neighborhood friends as well. So now whatever model you have, it would take care of two things: your social features as well as your user features. Okay, so now let's consider that after we concatenate all of them, so it would be roughly let's say a 10 dim vector or so. Now the question comes that what model we can choose to give this prediction to us. Okay, so the first thing is that pointwise similarity won't work. That is for sure. Now we know that if we try to represent every particular user into a node, means the whole social structure into a graph. Okay, let's say A and B are friends. A and B are friends, and this particular edge represents friendship. Friendship. See, this represents friendship. Similarly, C and D are friends. Okay, so and B or C are also, let's say, friends. Then there are very high chances that A and D should be also friends, right? So we need such a model which predicts whether there will be a edge between two particular nodes or not. And what are these nodes representing? These nodes are representing users. Okay, but how the data will look like, how this particular like how will even the model look like, what eventually we will train, all these questions will come in your mind. So let's try to decode everything one by one. See, the thing is that let's say this is at a particular time t, at a time t. Okay, and let's say at time t plus 1, the graph becomes this: A, B, C, D, B, C. Okay, now what does this mean? How can we take care of this? Means how do we convert this particular thing into something which we can use for model training? So we can say that, hey, the graph looks something at uh, time t, and these are the predictions at time t plus 1. Means at time t plus 1, B and D will have a connection. So there is a edge between them. So it means 1. A and D will have a connection. So again there is a edge between them. So again it is 1. Okay, and let's say if there is no connection, it means it's 0. Okay, so we get the labels now that okay, at time t plus 1, either it would be 1 or either it would be 0. So our motive would be to build a model where we give it a graph at time t. This is our model, and the work of this model is to predict whether there will be edges between two users at time t plus 1 or not. So whether there will be a edge between two users at time t plus 1 or not. Okay, but bhaiya, what are you even training? Like how will you say that B and D will be friends? So see, what we are going to do is that this is a particular node which is nothing but user features. We have another thing called as social features. Okay, which is nothing but these social features represent this edge features. Edge features. Whether there is a edge between two users or not, but the features will be always there. For example, if there is no edge between the users, there will be no relationship, but eventually the data could say that hey, they were in the same college, they were in the same company, but there were no overlapping years and there were no mutual connections between them, right? So the social features would be the edge features and these would be the user features. And using this, for every particular user, we will try to calculate embeddings. Okay, and let's say if we train our model, we get the embeddings for every particular user, right? So for embeddings for A, embeddings for B. Okay, now let's say this embedding looks something like this: 0.4, 0.6. For this it looks something like 0.8, 0.9. Okay, and once we do a dot product between them, we get a, and let's say if we do a after dot product, if the score comes out to we can apply softmax or sigmoid. We will apply softmax to convert this into a probability, and the score comes out to be, let's say, 0.86. Okay, and then we see, hey, whether there was an actual connection or not. So let's say the connection comes out to be 1. Okay, then it just becomes a classification problem, right? And for classification problem, we know that the loss function is binary cross entropy. But bhaiya, I still did not understand that how this thing will be converted into embeddings. So let's give an example. See, the formula could be really simple. Let's say there are 3 weight matrices: weight of self, weight of neighbor, and weight of edge. 3 weight matrices. Weight of self is something like 0.4, 0.6, 0.8, 0.5. I'm just taking an example. These are not real numbers. So this is 0.6, 0.4, 0.9, 0.12. And weight of edge could be something like 0.1, 0.5. Okay. So to what will the formula look like? Let me give you an example. This h of this h of u means the embedding of a particular user. Let's say a. H of a is equal to ReLU of weight of self into node features of a plus summation of weight of neighbor into node feature of that neighbor plus summation of weight of edge into edge of that particular neighbors. Now, what do I mean here? See, why did we do all the things? See, what do we want is that when we are seeing that hey, these two users can be connected or not, we want that all the other neighbors should be also considered, right? If we consider their mutual friends also, then we can make sure that we can make sure that we are giving them proper recommendations, right? So this particular thing, you see, weight of neighbor into node features of A, this will help in contributing. For example, if A is connected to C and B is connected to C, okay, so what we are going to do is when we are trying to calculate the embeddings of B, we would consider the weight of this quantity as well. So this will help in changing the embeddings of this particular thing, right? It will have some impact. And again C would have impact on A as well. And when we calculate the dot product between their embeddings that we get at in the final, then if the score comes to be high, then there are high chances that these two friends should be shown each other's recommendation, right? So now how will these embeddings look like? So for example, W self. Now W self was something like this, right? A 2 cross 2 matrix and node features of A. Now the node features, let's say there were multiple node features, but let's say there were only for now we can just say that only 2 features are there. Okay, so my calculation is easier. Okay, so 2 into 1, so it would be this quantity would come 2 into 1. Then for a particular user A is connected to C, so we will just see the weight of neighbor C. What is the weight matrix for that particular user? So it would be something like some 2 cross 2 matrix. And what is the new node features of that neighbor? Again 2 cross 1 matrix. We get some matrix from here. Okay, then again what is the weight edge? That is again a 2 cross 1 matrix, and this is edge of that particular weights. It could be just simply 1 into 2. Means I took a transpose of this edge features to just do multiplication. And then if I try to calculate all of the things, a matrix comes which has just like two quantities, let's say 0.8, 0.7. This embeddings comes out to be user A. Similarly, for user B, some embeddings come out 0.8, 0.9. And what we do next? We apply dot product. And to convert this into probability, you can apply softmax. So you get a score, whether they will be whether they will connect or not. And to take care of this score, so what for the loss function, you can apply binary cross entropy to update the gradients of these weight matrices. What are these weight matrices? W self, W neighbor, W edge, right? So this particular thing is called as a graph neural network. Graph neural network. Okay, now coming to the part where I'm going to tell you some few more things on how to handle imbalance data set. Now, why is this thing important? See, the thing is that you won't connect with everyone on the platform, right? It's not possible for you to connect with every person on that platform, right? So what you need to do, if I take one positive sample, then I should pass only 3 to 8 negative samples. Otherwise, if I just take negative samples only, that these users are never going to connect to each other at time t plus 1, then eventually my model will just say that no one is even going to connect with each other. We don't want that, right? So for every one positive sample, we are going to just take 3 to 8 negative samples, okay, to keep data balanced. And one more thing, see, positive samples would be less. So if my model is doing mistakes in representing that, hey, so let's say if my model said that, hey, these two people won't connect with each other, they won't connect, right? But at at time t plus 1 they did connect, right? So my model has to be harshly treated for that, means I need to penalize my model more. So how to take care of that? So for that, what you can do is that weighted binary cross entropy. See, what is the formula? W positive into y into log of prediction minus W negative into 1 minus y to log of 1 minus predicted. I guess this is the formula for binary cross entropy, right? So this WP, we will keep this value much higher as compared to W negative. Now why is that? If this value is higher, the loss would be higher, and if loss is higher, my grade means my model would penalize more. To make sure that next time you take care of such things where a positive sample doesn't go wrong, okay, so we would simply use weighted binary cross entropy. So I guess here I was able to cover all the things with respect to the model development. Now coming to the next part, that is evaluation. So for evaluation, see, there are two types of evaluation: online, offline. Now online evaluation means that, hey, your model is live and users are using it now, but how can you tell on the basis of that that your model is good or your model is bad? How? So for that, what we can do is that, let's say we just consider two matrices. First is number of connection requests sent in last 7 days, okay, and let's say number of the other matrix could be the number of connection requests accepted, because this is as useful as this won't give us all the details, but if the number of connection requests accepted are more, it means that we are able to show him proper recommendations accepted in last 7 days. So let's say you trained your model and then you just made it live, and after 7 days you see that there were like 10% increase in the number of connection requests accepted. So it means that your model is good, right? It has been performing good, so it shows relevant recommendations to everyone, okay. Now coming to offline evaluation. See, offline evaluation means that, hey, your model is not live, you have made the model, okay, but you want to know that whether my model is good or whether my model is bad, but you have historical data, so you know what is the actual results, right? So on the basis of that, you will be able to tell that whether my model is good or whether my model is bad. So first parameter you can think is precision at the rate k. So precision at the rate k means out of the k recommendations, how many did the user send the connection request to? So let's say you showed five 5 connections, sorry, 5 recommendations to that person, out of which you see that in the future, the data set you have with you, historical data, you see that 2 actually became connection, like proper. He or she sent the connection request to that particular users. So this is one of the key metrics. Second would be recall at the rate k. So here recall would mean how many of all possible new connections did we cover in the top 10 or top k. So for example, what does this mean? So let's say k is something like 20. Okay, just for this example, I'm taking k as 20. Now I know that in future the user sent like 5 connection request to let's say 20 out of these 20 users. So the recall score would be 5 by 20. Okay, then comes the most important metric, that is AUC, that is area under the ROC curve. See, why is this even metric important? See, these two things can tell you whether your model is good or not, but they don't tell you that the ranking quality. What do we mean by ranking quality here? So ranking quality means that a person, let's say, who is in the same company as yours, who is in the same college as yours, so there are very high chances that you connect with that person. So he should be ranked first, right? When I'm showing him, let's say if I'm showing 20 connections to you, so he should be at first, right? It should not be the opposite stuff. So how do we measure this AUC stuff? So simple thing is that how often does a positive edge get ranked more than the negative one? Let me give you a very simple example. So let's say rank 1, 2, 3, 4, 5. Use a, let's model predicted B, C, D, E, probability 0.9, 0.8, 0.7, 0.6, 0.5. Actual did not connect, did not connect, did not connect, something like this. So it means that my model should, for a particular user, let's say this user is Jatin. For Jatin, the predictions were made that Jatin would connect to A, B, C, D, E, and these were the scores. But in actual, Jatin just connected to B and Jatin just connected to D. Jatin did not connect with everyone. With A, C, and E, Jatin did not connect with them. Now, how would you calculate the area under the curve? So, see, for all the positive connections, so for this B, compare it with B, compare B with all the negative ones. So compare it with B, A, compare it with C, compare it with E. B score is 0.8, A score is 0.9, C score is 0.7, E score is 0.5. So for how many people like B score was greater? So you see 2. Okay, now take the next positive one, that is D. Okay, and compare it again with negative ones, C, E. D's probability is 0.6, A's probability is 0.9, 0.7, 0.5. For how many people 0.6 was greater? Only one. Okay, so total how many times you measured this? 0.8. So 6 times you did all these calculations, right? With 0.8 compared with 0.9, 0.8 compared with 0.7, 0.8 compared with 0.5, this 3, the same stuff, this 3. So total times you measured this? 6. Okay, and how many times you want? 3 times. So your AUC comes to be 3 by 6, that is 0.5. Now generally for a good model it should be greater than 0.5, because 0.5 just tells that the model is random. It is not that good. So if your model is perfect, it should be roughly 1. Okay, the score is as closer to 1, it's as good. So these 3 matrices can be used for your evaluation. Now, and this AUC matrix only tells you about the ranking quality, while precision at the rate K and recall at the rate K won't even tell you, would never tell you about the ranking quality. Ranking quality really matters. Then coming to the last part, that is the serving. See, generally we need to think it very logically here. So let's say if a user is coming, so would I compare this embedding with other billion embeddings? Just think logically. Would I do that? No. The answer is no to that. We need to decrease the sample size. Now, how would we decrease the sample size? See, generally what happens? This decreasing of sample size is called as candidate generation. Candidate generation. So, what does this mean? Here, I'm not going to use my model or anything like that, but I have to decrease this 1 billion to a quantity which is something where I can even put my calculations to. Okay, where I can apply my model to. So, see, generally what happens is that if A has a friend B, B has a friend C. Okay. Similarly, let's say D has a friend E, E has a friend F. This G has a friend H, and E and G are also friends. So E can also connect to H, D can also connect to H. So generally, what I mean to say is that rather than going to third degree connections, we can just think of friends here. So what do I mean to say is that rather than comparing it with everyone, I would just compare A with A and C's probability, D and B's probability, D and H probability, whether they would be friends or not, right? So how much the number of from 1 billion, how many numbers would decrease? So let's say on average, every person has 200 friends on average. Okay, so again, it would be for everyone. So 200 into 200, that comes out to be 4 lakh. So you see, from 1 billion, the data reduces to just 4 lakh. Now, I can use my model on this 4 lakh, 4 lakh people for my particular user to check who will be the top 50 guys, whom top 50 people whom I can recommend. Okay, so here the other thing is that if you start doing this 4 lakh calculations also on the fly means as soon as user opens the platform and you say that, hey, for Jatin, I'm going to calculate this embedding dot product score for 4 lakh people, and this would be happening for all the people around the globe, then you see the inference latency would be really really high. The latency to show the recommended users would be really really high. We don't want that. So what is the possible solution? The possible solution is that we do it batch computation. Means we already calculate the scores offline. Okay, and as soon as user comes online, we just show him the top 50 users, so the time latency would decrease. We are not doing it on the fly. We would save it somewhere and we would just show him when he opens the platform. So how would this whole serving look like? So there would be two things. One would be the prediction pipeline, and other would be the PYMK pipeline. Now let's discuss one by one about each pipeline. See this PY, people you may know pipeline. You have your data, right? It will be converted into features, right? Once converted into features, you have this scoring service. Now this scoring service uses your model, my model. But for this scoring service, first I need to decrease the data. For that, I have this FOF service, which makes sure that the data is reduced to only 4 lakh. So now this scoring service, what it will do? It will try to do the calculations of, let's say Jatin is coming. Jatin's calculation with 4 lakh users, and we'll try to see, okay, what is the probability scores. So there were 50 users whose probability scores was 0.9, 0.96, 0.95. So this scoring service would store all the things somewhere. PYMK stuff stored. Okay, now this is your PYMK pipeline. But what happens when a user comes? So that will be a prediction pipeline. So see, this is a user who is coming. Okay, this is the PYMK service. PYMK service. He would just call this particular stuff. Let me just draw it properly. PYMK. He would just call it and he would just get the data here. So you see, all the stuff is pretty straightforward and logical enough. Okay, now you can ask me one more thing that, hey, Jatin, a new user comes. How would you tackle that problem? So whenever a new, so what this problem is known as, this is known as cold start problem, because initially we won't have any data of this user. He won't have any connections also. He won't have anything other than the stuff that we would have his age, college, company, industry. We would only have these basic details. See, the first thing is, as soon as a new user comes, what you would you do is show him the most popular users. This is pure logic, nothing else. Show him the most popular people on the platform. Then let's say you showed him this, then you can show him people who are from his college. Once this guy starts sending connection request, then eventually itself there will be an embedding created. Whenever our model retrains in a week, automatically the embeddings will get updated. So next time the user will open his app, his embeddings would be updated and we would show him relevant recommendations. So this is how we solve the cold start problem as well. Okay, so this is the whole solution of people you may know. Thanks.